Okay. The minute... oh my god. I haven't spoken any words yet today. I just choked myself up there. Okay. Now, is this even readable? I don't think it is. I'm looking at the stream output. Oh, wait. It just suddenly cleared up a bit. All right. Nonetheless, let me try and make the text a little bigger. So, yeah, basically, a friend of mine sent me this paper. It's not really a field that I have any experience in, but we're going to try and read it and make as much sense of it as we can. All right. By fairly simple considerations of stability and multistationarity in nonlinear systems of first-order differential equations, it is shown that under quite mild restrictions, a negative feedback loop is a necessary condition for stability, that a positive feedback loop is a necessary condition for multistationarity. So, what is multistationarity? Oh my goodness. This is not helping. No, not multi-stationary. Well, I mean, I can guess what it means. I think it means having like multiple equilibrium points that you could fall into. Apparently, dynamical characteristics of complex self-regulating or self-organizing systems, such as the number of steady states, the number of stable states, the size of their basins of attraction, and the degree of structural stability, are intimately related to the number, types, and strengths of the feedback loops in the systems. Bunch of references. Well, we'll just keep reading. If stability is governed by the sign of the elements of the Jacobian, independent of their magnitudes, necessary and sufficient conditions for stability and instability in terms of loops have been given by so-and-so and so-and-so based on a theorem by others. However, a fundamental and general understanding of the relationship between feedback loop structures and dynamic behavior of complex biological systems is still lacking despite noteworthy contributions by Thomas and his buddies. Okay. In general, one finds that negative feedback loops promote stability, while positive feedback loops may generate multiple stable states. Hey, I think I was right. Either isolated points or limit cycles. Actually, I do know what limit cycles means. It came up in a course I took. A limit cycle is essentially if you draw the phase space of a differential equation, a limit cycle is a solution which forms a cycle, like a literal loop. It might be an amorphous loop, but still a loop inside the phase space. And not only that, the domain of attraction leads into that loop. It's not a unstable equilibrium. Anyway, in fact, for dynamic systems dominated by a threshold phenomena, it has been conjectured that a negative feedback loop is a necessary condition for stability, that a positive feedback loop is a necessary condition for multistationarity. Here we demonstrate formally that this is indeed the case for very general systems described by first-order autonomous differential equations. I don't know what autonomous means here, but anyway. Unfortunately, the phenomenon of feedback and feedback loops is often described in terms that may be somewhat misleading due to a lack of preciseness in the terminology. To be more precise, let us consider the system time derivative of vector x is some function of x. Of first-order autonomous differential equations, where the rate functions fi of x are c1, that is to say, differentiable with continuous first order derivatives. This is not nonlinear. Didn't they say, maybe they'll add it later, but yeah, they say nonlinear. This is 100% linear. Okay, so in general it can depend on x. Let ik be an ordered set of k different elements from 1 to n, and jk a permutation of ik, if the loop product is non-zero in at least parts of phase space, there is a simple or composite k-dimensional loop among these variables. Oh man. I do not have the background to understand what they're talking about here. Okay, let's do some drawing. Yeah. So let's do our Jacobian. I always forget the notation for the Jacobian. Whatever, I'll just put J. Okay, J. Oh my god, that's tiny. Well, there, we can do that. J equals, so for each of these, now I always forget which one's the column and which one's the row. I don't know if it matters. A sub ij, so the outputs are on, yeah, okay, yeah. So here we have, I'm going to call this d, I don't know, derivative of fi with respect to xj. All right, this is not a good font. Okay, I think that's fine. All right, well, okay, so actually, all right, this will be my template. Whoops. And we'll just fill in the numbers until I get the idea. Okay, I have too many here. I'm going to be here all day, so I'll just do a few. So these are all df1. And this is going to be x1, 2, 3, 4. This may seem like a waste of time, but it really is what I have to do, or else I'm just going to get lost in the notation. There's probably some like fancy latex way to generate this or something, but screw that, I don't have all day. One thing I do not miss from grad school is fighting with latex. My God. Everyone goes on and on about how great latex is. Latex has the same problem as Git. The only reason people use it is because it works. But other than that, it sucks. All right, so this is our Jacobian. And what they are saying is they're calling this Aij. Now this loop product, let's just do an example here so I can get the idea. So let's say I is equal to I don't know, let's just do a 3-element system, and we'll say this is 2, 3, 1, and J is going to be, I don't know, 3, 2, 1. Then the loop product is I can actually just grab them from here. So we need 2, 3. Oh, whoops. Again, this may seem like a waste of time, but anyway. So we have this guy. Times this guy times this guy. And what does this mean? Let me just draw them in here. Sorry to the colorblind people. So that one was this one. Also, and then this one was that one, and this one was that one. Again, my apologies to any colorblind viewers. Well, okay, I can maybe do a little better. Well, I can't dash it easily. Whatever. Let's move on. So what does this mean? It means that we're going to take exactly one from each row. We're going to take exactly one from each column. And then we're going to multiply them all together. I don't know what this means. If the loop product blah is non-zero in at least parts of the phase space, there is a simple or composite k-dimensional loop among these variables. Man, what does that mean? Well, okay, so let's not forget that by the setup of their system, just move this over here. In their setup, let's not forget that this is actually dx1 by dt. These should all be partial derivatives, by the way, but anyway, you get the point. So we have so let me just for sanity's sake reorder these so that they're in the order of yeah. I guess I should finish out this equation here. This isn't quite exact until you do this. I'm abusing notation just a little bit here, but so this is dx1, dx2. Well, I'm abusing notation a lot, but it bothers me that this equation didn't make sense. Now it makes sense, at least. All right, let's see if there's anything I can read about this. We discuss differential dynamics in terms of Jacobian loops, that is to say, combination of these signed Jacobian entries under permutation of the indices. We analyze conditions of their dynamical roles, necessary and sufficient conditions for loop stability and instability, as well as conditions for exchange of stability. I don't know what this means, but the rest of it sounds useful. It also doesn't seem like it's going to be that easy to read. U Montreal, huh? This looks like an undergrad paper. I don't know what CRM is. Consider a dynamical system described by the differential system, blah. Or equivalently. Okay, so these are parameters of the system, which we could just imagine as being part of the function, but they wrote it out explicitly for some reason. The component functions fi are assumed to be at least C1. That is differentiable. Oh, right. I mean, I've forgotten what all this notation means, but I think this just means that the derivative is the derivative is continuous. Anyway, the partial order relation defines the vector order in R of n. I don't know what that means. Solving blah equals 0 yields the equilibria of the system for the parameter value k. Let phi of t be the flow associated with 1, 1. Associated with 1, 1, that is, phi of t is a solution of 1, 1 based at x. The equilibria are fixed points of the flow. System in 1, 1 is said to be monotone increasing if the flow preserves the order O for positive time. Oh my god. I do not have the background to read this. So I think this means the vector x is less than or equal to y if and only if every element of x is less than or equal to every element, or to the corresponding element of y. So that means that if some elements are bigger and some elements are smaller, then I guess neither is less than or equal to the other. So there is no defined order in that case. I mean, this is a partial order. Anyway, the equilibria are fixed points of the flow. It is said to be monotone increasing if the flow preserves the order. Okay, I see. I think I understand. So like what that means is taking our vectors to just be a single variable for a second. It means that if I start higher, I will stay higher. So this is x and y. I think that's what that means. I don't know what that is interesting for, but whatever. The general Jacobian matrix at x is given by this expression. There's so much notational clutter here, but anyway. And in general depends on the state variables, except for linear systems. Yes, that makes sense to me. We recall the following definitions. An equilibrium is stable if every nearby solution stays stable for all future time. This is really sloppy. Um, if in addition x of t converges to x bar, the equilibrium is said to be asymptotically stable. Yeah, anyway. The equilibrium is unstable if there is a neighborhood W such that every neighborhood W1 in W contains at least a solution x of t based in W1, and that does not lie entirely in W. Man, it's so hard to read this stuff. So let's give ourselves a W, and we have the equilibrium. So I guess x bar is going to be our so-called unstable point. And what this means is for any W1 that you can draw in here, no matter what you make it, I can always find a point in W1 whose solution exits that does not lie entirely. Oh, it even exits W. I don't understand this W1. Like, oh, I think it means that, well, if every W1, every neighborhood in W1, okay, so there is no specific x bar actually. But if every possible neighborhood exits W, then isn't it equivalent to say that every point exits W? Unstable if there is a neighborhood W such that every neighborhood in W contains at least a solution, blah. Based in W, I don't know what based means. I assume it just means like the initial point is in there. And it does not lie entirely in W. Oh, so it is allowed to go out and come back, but I don't know, man. Let's just keep reading. A closed orbit, what character is this again? Gamma. Gamma of t is a non-trivial periodic solution of some period t. It is asymptotically stable if every neighborhood W contains a neighborhood W2 such that the solution of all the points in W2 is a subset of W1. This W1? Oh my god, dude, this paper is not that good. The equilibrium x bar is hyperbolic, that is to say a sink or a source, if every eigenvalue has a non-zero real part. Equilibrium closed orbits are the simple dynamics or limit sets of a system. A trajectory gamma of t. By the way, I'm told that in Greek you would actually pronounce this as a gamma, something like that. Anyway, a trajectory gamma of t is stable, that is to say, what does resp mean? I'm just treating that as IE, but whatever. Oh, respectively. Oh, wait a second. A trajectory is stable or asymptotically stable. Okay, let's read both sentences. A trajectory is stable if it remains over time in the vicinity of simple dynamics, and a trajectory is asymptotically stable if it converges over time to simple dynamics. Fine. The basin of XB is the open set of all solution curves converging to X bar. Or, okay, we called this domain of attraction in our class. I guess this is a kind of a play on words there if we call X bar a sink. Anyway, the index of X bar is the number of eigenvalues counting multiplicities. Man, I hate when they just drop this eigenvalue crap on you, and it's like, well, where did that come from? Like, the following characterization theorem is also well known. Yeah, well, speak for yourself, but anyway. If the equilibrium x bar is stable, then no eigenvalue of the Jacobian at x bar has positive real part. A hyperbolic point is either unstable or asymptotically stable. A saddle point is unstable. All right, let's think about that for a second. So if we just imagine the neighborhood of x bar, so let's say this is a stable point. If you're quote unquote really close to x bar, then we can pretend that the Jacobian is linear. In other words, we can linearize around this point. Now, the whole, spiel about eigenvectors is that if I take, any dx, right? Now, I drew it up here. Wait a sec. This is not correct. This is what is this left-hand side supposed to be? This is not correct at all. Wait a minute. And but none of this is, what am I even writing here? This is just, now hold on. Where's the time element? We need a dt. So, okay, this left-hand side is definitely supposed to be dx1, right? Like, in other words, like, or I'll call it delta x1, but I don't have a delta, so I'll just stick with dx for now. Oh, I see what I'm missing. I see. You need, yeah, I see what the problem is now. You need to evaluate this at x, and when you evaluate that at x, this is almost like embarrassing. I swear I did this stuff in school, but it's been so long. I mean, I know intuitively, like just based on like my memory and feeling from having done this kind of thing before, is that the Jacobian, if you evaluate it at a point, you just get a matrix of scalars, and what those scalars represent is like the linearization around that point. Now, man, I gotta go like way back to the beginning here. So we got dx by dt is equal to f of x. And what we have done here is we've expanded out all of the partial derivatives into a matrix. And what does this mean again? God. By the way, this buddy who sent me this paper, every now and then he'll just name drop Jacobians and eigenvalues in conversations we're having, and then my brain goes into overdrive trying to remember like what on earth it all means. And I'm just trying desperately to follow what he's saying. So if I wanted to do, like if I wanted to just calculate a small dx, right, I would do f of x, like you could replace these d's with deltas there, but f of x times dt. And that's what I was trying to write down with the Jacobian here, but this like just is nonsensical what I was doing. Like I'm trying to figure out what on earth. I don't understand. Why do we even care about the Jacobian? Because like if I wanted to linearize around a point, okay. I am going to pull up a textbook. Hold on, I gotta find it here. Where is that? Okay, found it. So it's in this folder. How come I couldn't find it? Oh, here it is. Okay. Now I have the link. Now, Professor Maggiore, who by the way is awesome. He's really good. He wrote this textbook, and it's very useful. It's one of the best textbooks actually I've ever encountered for like basically dense mathematical stuff. I mean, Professor Maggiore just did a really good job of keeping all the mathematical rigor so that it made sense and was self-contained, but without without doing this, okay, without just vomiting words on the page and basically just like, you know, um, like dropping big jargon and all that, like it's actually readable. I mean, I wouldn't say it's easy, but that's because the material isn't easy. Now, Professor Bajori specifically did ask that we not share this textbook, so it's probably not great that I am looking at it while streaming. Uh, but on the other hand, I'm not going to show you the whole textbook. I basically just want to see like the setup and where the Jacobian comes in. And, you know, you might even be able to get this as a preview if you looked on Amazon anyway. Okay. So here's the mathematical setup. The setup that Professor Majori used was like airtight. It made perfect sense. It didn't have any like weird quirks. Like, it was really good, and I'm really struggling to remember. Anyway, solar system, rigid body, electrical circuit, and motor. The physical processes whose evolution is time is mathematically described by an ODE. In this chapter, we introduce ODEs, focusing on the problem of existence and uniqueness of their solutions. To the right-hand side of an ODE, one associates a geometric object, the so-called vector field. Vector fields are collections of velocity vectors, each one attached at a different point of the state space of the ODE. Vector fields and ODEs are mathematically equivalent objects. Interesting. I remember this. We did that stuff with the tangent bundles. Anyway, in this chapter, we show that the collection of solutions of an ODE gives rise to a deterministic dynamical system. The approach taken in this chapter is inspired by Arnold. Additional references are that and that. This is rather advanced. that, and that. In particular, the material in sections 1.3 is adapted from this. Okay. An ODE is an equation of the form blah. He allows it to be time, what's the word? Time dependent. The vector x is called the state of the equation. The set script x, where the state x lives, is called the state space of the ODE. Finally, the vector function f, taking potentially the time and element of the state space to a member of Rn, is called the vector field associated with the ODE. This chapter presents basic properties of the solutions of ODEs and prepares the reader for the more advanced treatment of chapter 2. The main concept of this chapter is that ODEs, whose right-hand sides are locally Lipschitz continuous functions, give rise to deterministic dynamical systems, processes that evolve in time in a predictable way from an initial condition. The formal definition of dynamical system will be given in 1.6. For now, we introduce the idea with an example. I'm going to skip this, although I shouldn't skip this. This has two basic properties. It's consistent. Okay, yeah. Even if it is time dependent. Wait, no, hold on. Yeah. If you start at time equals 0 at x0, then you had better be at x0. Yeah, this identity is called the consistency property. The second property is deduced through an elementary experiment. After s units of time, the state of the point mass is equal to phi s of x naught. Oh, interesting. Yeah. So this is the, there's some fancy math term for this, but essentially what this means is if I start at x naught and I travel for t plus s seconds. Oh, wait a minute. I thought this was time dependence. So the solution, if I start at x naught, wait a sec, This is not the time dependence. This is the... No, this is the time dependence in F, but the time argument to the solution is elapsed time, I think. Maybe. Okay, well, let's just ignore the time dependence in the definition of the ODE and pretend it's not there, because the time argument of this phi function, which is the solution function, means start at x naught and travel for this much time. And essentially what this is saying is, if I start at x naught and I travel for t plus s seconds, I had better get the same result as if I first go s seconds and then go t seconds, which makes sense. Group property, yeah. This is what makes it associative. As it turns out, the consistency and group properties are used to define deterministic dynamical systems in a very general sense, and the solution map phi is called the phase flow generated by the ODE. These notions will be formalized. Okay, here we go. A vector field on Rn is an assignment to each point x in Rn of a geometric vector in Rn with origin at x. Given two vectors, the associated geometric vector at x, vx, is defined to be the bound vector whose tail is at x and whose head is at x plus v. The geometric tangent space to Rn at x, denoted Txrn, is the collection of all geometric vectors. The geometric tangent bundle of Rn is the collection of all geometric vectors at arbitrary points. The sets just defined have a natural real vector space structure. If Vw are in the tangent bundle and lambda is some real number, we define v plus lambda wx to be... Oh, you just do it for each component. I see. Yeah, okay. Okay, yeah. Moreover, if v and w are in the tangent bundle, we define vx plus lambda of w1. Wait a minute, I thought I understood this, maybe I don't. The geometric tangent space to Rn at x. Oh. This is not the tangent bundle with the subscript x. If vxwx is a member of, or are both members, okay, they're not ordered pairs. If they're both members of the tangent space at x, then we define their sum to be the sum of the vectors positioned at x. And if we have two vectors starting from different points, then we define their sum to be the sum of the vectors at the sum of the base points. Okay. With this structure, Txrn is isomorphic to Rn through some isomorphism that I don't particularly care about right now. An autonomous vector field on script x is a function such that it remains in the tangent space. A non-autonomous, oh, okay, so time-dependent vector field such that f is, okay, fine. Now, where does the Jacobian come in? That's what I need to know. Also, my the thing I was listening to just finished, so I'm going to put on something else. Oh, no, it didn't. There was just a really long silence between songs. Okay, in definition 1.3, a vector field f is a function between an open set and the tangent bundle. Yeah, that's fine. I'm skipping stuff, as you can see. Let f be a vector field. The referential equation is the ODE associated with f. Okay. an orbit of f through x naught is the set O. Okay, I need to read this. Let f be a vector field with x an open subset of Rn, and let x naught be a member of x script x. A differentiable curve gamma from the tangent space at x naught mapping to wait, what does that notation mean? Yeah, I thought so. Wait, what is that? T sub x? Oh, where T sub x is a real number, is an interval containing 0. I don't understand why we need to do that. I think this is just like a time. Like, yeah, I think what this means is all of the defined times in the solution starting at x naught. Anyway. So this function taking the time to a state space member is a solution with initial condition x naught if, that's what I get for skipping the definition, is a solution of that given with initial condition x naught if we start at x naught and x of t is differentiable, and for all t in the allowed times, the partial derivative, or I guess the full derivative, is equal to the function evaluated. Yeah, okay. Okay, a differentiable curve gamma taking a time to a state space member with the valid times containing 0 is an integral curve of f through x naught, is said to be an integral curve of f through x naught if gamma of t is a solution with initial condition x. Okay, an orbit is the set O of x naught is equal to basically the entire state space, where, in other words, you plug in every single allowed time into your solution function, and then you draw that curve, integral curve. The set O plus is a positive semi-orbit. The set O minus is a negative semi-orbit. Okay. Geometrically, an integral curve of a vector field is a parametric curve whose velocity vector at each point coincides with the evaluation of the vector field at that point. An orbit of f, being the image of an integral curve of f, is an unparameterized curve in x. Fascinating. By definition, this curve is everywhere tangent to the vector field. Yeah, okay. Yeah. Yeah. The previous example illustrates a vector field whose solutions are defined for all t in the real numbers. Generally, solutions may only be defined on a subset of the real line. Okay. Consider the vector field defined as x squared, which gives blah. Solving for x, we get blah. For each x naught, the map. Oh, hey, this is one of those ordered ones, as the other paper was saying. We see here that solutions with non-zero initial conditions are only defined on a subset of the real line, and they blow up in finite time. This phenomenon of finite escape time will be discussed in 1.4. This is, by the way, why we can't just take t be a real number. It has to be in that special set. The domain of definition of the function phi tx naught is a subset of r squared depicted below. That's interesting. Since phi is not defined on the entire real number space, it is called a local phase flow. The formal definition of this concept is presented later. I don't care about this right now. Well, I mean, it's not that I don't care, but I really just need to see what the Jacobian does for us. The Jacobian, as Professor Majori would say. And then I'm remembering the lectures. He was so good, man. He was so good. Okay. Um, so this is a linear differential equation. The vector field, first using the fact that the map X is continuously differentiable and its Jacobian is A. Since the norm of the Jacobian is this theorem 8.51 assures that the vector field is globally Lipschitz. Oh boy. Well, this was less helpful than I thought, but at least I feel a little bit more grounded in parsing the notation and all that. So let's go back here. I mean, if, for example, I is 1 to 7 and j is blah, p of ij is rearranged to p of ij equals blah. I'm noticing that putting the same indices side by side here. Can we always do this? Okay, so in this particular example that I picked, I made one loop here and one loop here. Does he enforce that? Yeah, he doesn't enforce that the i's and j's can't be equal. As there is only one closed chain of indices, not in general, but in this example, this represents a single loop which can be written as blah. On the other hand, if j is blah, a similar arrangement gives, yeah, you can have two loops. This is the product of two simple disjunct loop products, and the corresponding loop will be termed a composite loop. Thus, the loop products of a composite loop is simply the product of the component loop products. The condition 2.3, literally speaking, links the factors in the loop product space together. Oh no, this special definition links the factors together in a simple loop product or a product of simple loop products. If j equals is for some s less than r, then there is a simple loop with r minus s plus 1 elements, and the next factor is the first factor in a simple loop. If, however, j is not a member of I1 to r, okay, whatever. This doesn't seem that profound. Each variable in a feedback loop exerts an indirect influence on its own subsequent development as well as that of the other loop variables. Man, I don't understand why though. Because, right, this, the thing we're interested in here that lets us even think about this at all is that we've got the time derivative on the left-hand side is the function of the right-hand side. What does the Jacobian do for you here again? Man, I thought I understood this at some point in my life, but I definitely don't anymore. Man, I'm really trying to understand what this means. All right, let's try just a general Google search. Using Jacobian for ODE solving. Let's see what that brings up. All right, this looks useful. All right, hold on. Let's just watch it. I gotta pause the music I was listening to there, and then I gotta go into here, turn on the sound. I hope it's not too loud.
Here, let's consider the
loud.
system of nonlinear equations. X dot, or dx dt, is equal to x times 1 minus x minus 2y, and y dot equals y times 1 minus 2x minus y. So what I want to do here is to find all the fixed points.
I like this guy's
and
accent.
determine their stability. Okay, so this is some function here of both x and y, and this is some other function g, let's call it, of x and y. So to find the fixed points, we set f and g to 0, right? So you set f equals 0 and g equal to 0. So what are the fixed points here? So we can read off some of them, right? So let's say x star and y star is the fixed points. Certainly 0, 0 is a fixed point. If x equals 0, then f is 0. And if x equals 0 and y is not equal to 0, then 1 minus y is supposed to be 0. So y is 1 is a fixed point. And the other one is if y equals 0, right? If y is equal to 0, g is 0. And if y is equal to 0 and x is not 0, then 1 minus x has to be 0, or x is equal to 1. Okay? So those are three rather simple fixed points. The last fixed point can happen if both x and y are not 0. So if both x and y are not 0, then we must have x plus 2y equal to 1, and 2x plus y has to be equal to 1. So the fourth fixed point, or so let's just say the fourth fixed point satisfies, let's look at that again, x plus 2y equal to 1.
Whatever, man.
Or
just solve your system.
Times. And then the fourth fixed point here.
Whatever.
J is in a 2x2 system is the matrix partial of f with respect to x, partial of f with respect to y, partial of g with respect to x, partial of g with respect to y. Okay? And the Jacobian matrix determines then the stability of the fixed points. If the eigenvalue, so you evaluate the Jacobian matrix at the fixed points, and if the any eigenvalue has a positive real part, then the fixed point is unstable. If all the eigenvalues have negative real parts, then the fixed point is stable. Okay, so we have f and y. So
well, why is that?
X minus 2y.
Like, I don't need a rigorous mathematical proof, but I really want to know why he thinks that's true. Maybe I can intuit it just by. Nah, no way is this gonna help. All right, it is the ultimate guide. Must be good. Blah, blah, blah. For a robot that operates in 3 dimensions, the Jacobian matrix transforms joint velocities into end effector velocities, and I'll show you an end effector, using the following equation. What the heck is this? So this omega is probably the rotational speed. What is this Q? Q with the dot on top represents the joint velocities. Oh, joint, not like joint as in together, joint as in like a joint. Is there anything for a revolute joint? Oh, Lord. I see. So if you have some arbitrary robotic arm with n joints, and this is talking about the speed and rotational velocity of like the end of the arm, like the hand of the arm, so to speak. Oh, hey, you want to buy some Lego? Anyway, the size of this vector is n by 1, with n being equal to the number of joints. Okay, yeah. Note that Q can represent either revolute joints or prismatic joints. Now I want to play Risk of Rain too. Anyway, focus. J is the Jacobian matrix. It is an m rows by n columns matrix and represents a number of joints. The matrix represents the end effector. X, Y, and Z with the dots on top represent linear velocities, angular velocities. Okay, I figured all that out. Consider this scary arm. The equation using the Jacobian would be as follows. Wait, what? Hold it, hold it, hold it, hold it, hold it, hold it. But this is so okay. In here, what I'm talking about, my inputs, right? Like my x here, which is an input to f, is the same. Like dx dt is what's on the left hand side, right? So in his system, right, he's got that x, y, and z. He's got that x, y, z is some function, I'll call it, I don't know, t, of, q1, q2, and so on, right? But for me, in this paper that I'm desperately trying to make sense of, I mean, I haven't even started reading the paper, basically. I'm still just trying to fill myself in on the background. But in here, like, so I guess this is dx1 by dt, and this is also dx1 by dt, or right? Yeah, because this is the chain rule at work here, because this left hand side here, this left hand side is dx1 by dt, right? But it's some multidimensional function of all the inputs, and if I do the chain rule, or the multidimensional chain rule, like this is what you get. Yeah, so this is why I couldn't think of what on earth to write inside here, because like I was thinking, like, well, we want to find the time derivatives. We don't already have them, but we need to already have them to find them. Or to be precise, so you evaluate this at x. Ah, I see. So let me write this out in matrix notation here. So if I have x is equal to ax, then what I can do is a minus the identity of x equals 0. And I guess this is how I can solve for x. And this is probably where the eigenvalued stuff comes up, because this a minus I comes up when you're dealing with eigenvectors. So this is what I would do if I was solving for the time derivative, but that's not what we're doing here. He's using the Jacobian to basically encode the multidimensional chain rule. How to find, I don't care about that right now. Oh, actually, this is kind of cool though. Actually, this is super cool. This is the kind of stuff I really liked in school, but I never understood it. Like I never, because the profs I had for, well, the prof I had for controls in undergrad was just piss poor, let's be honest. And try as I might, I never, like all of my friends thought I was being stupid because I would stay up late with the textbook trying to make sense of what on earth the professor was talking about and just not getting it. And there was one time what exactly had happened? There was like one last assignment for the course, and I had spent hours and hours and hours trying to do it, just did not understand. And my buddy was like, yo, you need to prioritize. And he said, here, I found the solutions to this textbook online. Because the prof, of course, being a bad prof, I mean, this doesn't mean you're a bad prof, but pretty much all bad profs, instead of making an assignment, they'll just pick problems from the textbook and give them to you and be like, whatever. And some good profs give questions from the textbook though too. Like for example, Professor Majori would give us problems from his textbook, but they were good problems. Anyway, what had happened was I had managed to get like 1 out of 4 questions on my own, and the others I was just desperately stuck. And in the end, I just copied the answers out of the textbook and submitted that. It's the only time in my entire school career that I ever copied an answer. And I kind of got talked into it, but I was also like kind of weak at the time because I'd been fighting with this course all term long and not getting it. And I was like, forget it. And that's what I did, and I felt really guilty about it. But to look back on it for a second, it's like, well, anyway, that's just what happened. I told the story, so there. Okay. I'm getting off on a tangent here, no pun intended. So what this guy's saying is that the point is stable if the Jacobian has negative eigenvalues. Why should that be the case? Why? Let's think about it. So what the Jacobian tells us is that if I step some amount dx in any direction, let me draw it on an angle here just to imply that I'm not axis aligned. If I step some dx in any direction, then the time derivatives so the change in the time derivatives will be the Jacobian. Is that right? Like let me get myself a delta character here. So the change in the time derivatives is equal to the Jacobian evaluated at x bar, which I'll draw in, times the Jacobian evaluated at x bar times, so I shouldn't call this dx, I really wanted it to be delta x. Okay, so the change in the time derivatives is the Jacobian matrix evaluated at this point times this little change here. Well, what does that tell us? Like, why is it positive and negative? Shouldn't it be magnitude less than or equal to 1? What did he say?
Then the fixed point is unstable if the stability vector x partial g with respect to y. Okay, and the Jacobian matrix determines then the stability of the fixed points. If the eigenvalue, so you evaluate the Jacobian matrix at the fixed points, and if the any eigenvalue has a positive real part, then the fixed point is unstable. If all the eigenvalues have negative real parts, then the fixed point is stable. Okay, so we have.
Right. Of course. Because now what we have. Yeah. Okay. All right. Okay. It makes sense now. I finally understand. Because when you do the solution, because this is now a linear ODE, and when you do the solution of a linear ODE, it is well, things get a little tricky when you have repeated eigenvalues. I kind of forget how that works. But when you do I might actually do this by hand here in a second if I feel like I need to, but when you solve a linear ODE, the general solution is something along the lines of, so phi of x is something along the lines of e to the, this is a complex exponential, by the way, e to the, I'll just call it, well, L1. Does this work? No, it doesn't. E to the L1 t times some constant, so I'll call it k1 plus k2 times e to the L2 t, etc., right? So, okay, that's why they have to have negative real part, because otherwise this solution blows up. Right? But that's in a one-dimensional case. How does this work? I forget how this works. You see, I was so frustrated when I took the differential equations for engineers course, because it was the most frustrating, like, rote memorization course you could imagine. It was just like, here's the procedure, do the procedure, stop asking questions. I don't have time to answer your silly questions. That's what it was like, and it really ticked me off, but anyway. This isn't quite right here, because all right, what's that? Paul's calculus notes, is that what it's called? I haven't looked at that for a while. Where's the, okay. Okay. Linear differential equations, blah, 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 blah. Oh my God. No, this is not what I want. Where's multivariable? Oh, here we go, systems of Ds, that's what I want. Eigenvectors, whatever. Okay, here we go, systems of ODEs. Coupled, that is fine. Man, I'm so rusty. Actually, I always forget what these mean. Homogeneous if the right hand side. Yeah, okay, fine. Solutions. Now that we've got some of the basics out of the way, solve the system. Now, if we start with n equals 1, the system reduces to a fairly simple linear first order differential equation. And this has the following solution. Yes, fine. So let's use this as a guide for general n, and let's see if blah will be a solution. Note that the only real difference here is that we let the constant in front of the exponential be a vector. All we need to do then is plug into this differential equation and see what we get. First, notice that the derivative is x prime of t. Okay. So upon plugging the guess into the differential equation, we get, oh, interesting. Now, since we know that exponentials are not 0, we can drop that portion and see. Ah, fascinating. Yeah, so this is exactly the equation for eigenvalues. So here, you see, this is what I've always been frustrated by this eigenvector, eigenvalue crap, because, like, people raise them up on these high pedestals of mathematical elegance, and yet they're so, like, abstract. Because like in this case, it just so happens, you know, if you do the algebra, oh, look at that, the eigenvalue solves the expression. Whoop-de-doo, right? But in other cases, the eigenvalue does have a geometric interpretation. It kind of hints at you like how big vectors get when you multiply them by the matrix. And when you're talking about like matrix norms, for example, the induced norm, it is very much related to the eigenvalues, right? So like sometimes it has geometric meaning. In this case, I don't think it does. It's just like the algebra says so. But everyone will be like, oh, look, it's an eigenvalue. Let's call it an eigenvalue. It makes me sound smart and like a mathematician. Anyway, so, okay. Now, what I wrote here is not quite correct. Instead, each of these are vectors. Well, it's almost correct. Also, I'm getting text messages about my plans later today. I should check. Yeah, okay. So, finally, we can say if the Jacobian has positive real parts, then the solutions starting at x bar will blow up and if not, they blow down. Although this is confusing to me because if it blows down, wait. Oh, there's the homogeneous solution that blows down, but then the forced solution, right? Oh. Oh, man. Oh, I'm so rusty. Well, it's a little bit inaccurate to say I'm rusty. It would be more accurate to say I never really understood this properly in the first place. Let me see if he's got an example here where it doesn't just die down to 0. As generally, the eigenvalues and eigenvectors see in a couple sections. Here are the few more phase portraits. You can see. Yeah, they all converge to 0, so then whatever, oh, this is an annoying, yeah, this friggin' like just comes out of nowhere, and it's like, what the heck. Here we go, non-homogeneous systems. Wait a second though. Because like, I don't get this though, because if I take So this has nothing to do with this delta x. Like all this stuff I drew out with delta x's just means nothing at all. It means nothing. Basically, if I just take the Jacobian at this point, the whole reason to take the Jacobian is because it solves the linear ODE, right? So, you know, we have some crazy phase space, you know, maybe it does that and does this and, you know, like that, you know, it's some crazy thing, right? But in the neighborhood of this point, if we take the neighborhood of this point and linearize it across the whole space, what does the phase space of a linear system look like? So, okay, for every point in the phase space, right, I can associate with it a derivative. I have a vector field, right? You know, so maybe it looks like this, like that. And if it's linear, oh, duh. All right, I see it now. I see now. If I am doing a linear approximation around a point, all right, let's do it in 1D first, and then I'll write down the multi-dimensional expression. Like, so f of x is roughly equal. What the heck was that? Anyway, is roughly equal to f prime at xa times x minus xa plus f of xa, right? And then in the multidimensional case, this becomes the Jacobian, and this is just, you know, the original point. So yeah, that's why tending to 0, the Jacobian tending to 0, because we're plugging in this x minus xa. So what it means is if I take the homogeneous solution, wait, what does the homogeneous solution mean here? Oh man. I gotta like redo my ODEs course and my controls course and my nonlinear controls course. I gotta redo all of them because I never understood them, not fully. Anyway, now I have a better understanding of why the Jacobian evaluated at a point has a meaning about whether or not it is stable. So now maybe this makes more sense. Okay, let's draw out, you know, a system of like nodes and relationships, right? like in example 1. Well, actually 3 is probably enough, or else I'm going to be here all day writing out like matrix terms. And what I'll do is I'll draw that if an arrow points to a node, I'll put so I'll call this K. I'll just call these I don't know, P, Q, R, and S. And this is going to be, I'm going to call them X, Y, and Z. It's easier to use single letters, especially because it's hard to do subscripts in XCali Draw. And what we have here, so what I'm using, let's start with linear systems, okay. What I'm using this to mean, this is a diagrammatic way of writing that dx by dt is going to be the sum of all the incoming nodes at times the relative, so py plus rz. I think once I've written it down here, it makes sense, right? So the dx by dt is going to be py plus rz, and we can do this for all of them. Dy by dt is equal to sz, and dz by dt is equal to qx, right? Now here I've deliberately drawn a loop so that I can try and get a handle on what on earth this loop stuff means. So our Jacobian is zero P R 0 0 S Q 0 0. Okay. Now. What is it they say? So if I find some loop product, which I still don't exactly know what on earth this is trying to get at, but it seems they're calling it that because they're probably implying that it has to do with these loops in the diagram, but so let's deliberately take the loop product here that corresponds to this loop. So let's call our I is going to be I'm just going to call it 1 3 2, or no, let's do I is 1 2 3 and do j is equal to 1 3 2. Oh no. So 1 has to connect to 3, 2 has to connect to 1, and 3 has to connect to 2, right? So our loop product, how did they notate this? Like that. So our P of I, j is equal to partial of x with respect, well actually, so let's call this fx, or like f sub x, f sub x, oops, we'll call this f sub y, we'll call this f sub z. So this is actually derivative of f sub x with respect to z, right? Plus the partial of f sub y with respect to x, plus the partial of f sub z with respect to y. I'm missing the d's in the denominator. And this is just equal to, so the partial of fx with respect to z is r. Oh no, this is a product, not a sum. R times partial of fy with respect to I think this needed to come from 2. So the x is driven by y is driven by z, and then z is driven by x. I think I needed to do this. So actually this should be that. This should be that. That should be that. And finally, what this does is dfx by dy is p times dfy by dz is s. Oh yeah, s. Times dfz by dx, which is q. Pumpkin spice latte. I don't know. Okay. Now, what do they say about this loop? The condition 2.3, I don't care. Each variable in a feedback loop exerts an indirect influence on its own subsequent development as well as that of the other loop variables. As is well known, speak for yourself. This influence is either positive or negative and the same for all variables in the loop. Accordingly, loops can be characterized as either positive or negative according to the sign of Pij. All right, fine. We're still making definitions. So here, depending on what P, Q, and S are, wait a second though, because if just one of them is negative, like if P was like negative 0.001 and then Q was like 1,000 and S was 10,000, then like I would still call that positive feedback. Or oh no, maybe not, because like as Y gets really big, X is going to get really small. Interesting. All principal subdeterminants of A. Fuck, man. Now we're not only are we bringing in determinants, which is my other pet peeve. Eigenvalues determinants are my biggest pet peeves in math because people just like casually drop them as if they know what they're talking about. But now we've got subdeterminants and principal subdeterminants. Like, get out of here, man. All principal subdeterminants of A can be written as a sum of loop products. This relation between determinants and loops has apparently been discovered independently a number of times, but does not appear in the generally available literature, says so-and-so. As it appears that so-and-so's words are still appropriate, we present their results in a new fashion. Let D, oh my god, all right, let D of I sub k be the k-dimensional principal subdeterminant of A, consisting of the indices in ik, which is defined as what does this even mean? Where epsilon is the number of even-dimensional component loops and the sum is over all k factorial permutations of I sub k. Okay. What is this, man? I mean, this is page 3 of 5. There's only 2.5 pages left. I don't have the background. What the principal subdeterminant? What on earth does that mean? Pages. It is shown that one of the principal submatrices of an incidence matrix without 0 rows is a permutation. What on earth, dude? What is a subdeterminant? I hate determinants. The determinant of a matrix obtained in this, okay. The determinant A of a matrix is a single number calculated by sum of the diagonal products in special fashion. I mean, so they've restricted themselves to 3 by 3 matrices. Look at the written matrix A above, and you see that you start by doing the products going down diagonally from left to right. This sounds more complicated as it is. Graphically, it looks like this. Huh. Interesting. The determinant of a matrix obtained in this way is a number that comes up a lot in all kinds of matrix operations. The same is true for a related quantity, the subdeterminant aik of the matrix A. There are as many subdeterminants as there are elements in the matrix aik. In the matrix, aik is obtained by erasing the line in the row that contains the element aik and calculating the determinant of the matrix that remains, and multiplying the number obtained by -1 to the power of I times k. With the concept of a subdeterminant, you can also define the rank of a matrix. The rank of a matrix is the number of rows or columns of the determinant or largest subdeterminant with non-zero value. Whoa. I didn't know that. I didn't know this formula. But still, I ignore the deep meaning of determinants because to me it's been presented as, here's the calculation for a determinant, and that's it. Like, no one ever showed me, like, well, so Sal Khan has a video on deriving the determinant for a 2 by 2 matrix, which he does by inverting the matrix by hand, like by doing algebra, and observing that the determinant pops out of the algebra. But that, to me, is just algebra. Like, it's just manipulating symbols on the page, and I find it hard to really draw any meaning from it. So then, when people say things like, oh, hey, you can calculate... Oh, wait a sec, is this Cramer's rule? I haven't seen it written like this before. Anyway, but when people say, like, oh, you can invert a matrix by taking subdeterminants, it's like, what? Why should that be the case? Like, what does that even mean? Like... What is that well-known thing they talked about? As is well known, this influence, all principal subdeterminants of A can be written as a sum of loop products. Bunch of references. And am I really going to sit down and read these references? This relation between determinants and loops has apparently been discovered independently a number of times. Okay, so they're going to explain it, I guess. Given some permutation ik, we do all of the permutations jk, and we calculate these loop products and something, something, multiply them together, -1, blah, blah, blah. Also, let sk, oh yeah, so this will be 1 for the whole matrix. As -1 to the k, sk is the coefficient of lambda to the n minus k in the characteristic polynomial of A. What? What? Ruth Hurwitz, geez, I haven't heard that in a while. I forget actually what that means. I'm sure it'll come back to me. Oh, right. Um, right. The eigenvalues, because necessary and sufficient conditions for the eigenvalues to have negative real parts and imply that. I'm so lost. Hartman Grumman, it's just name dropping all this stuff. I don't know this stuff, man. I don't have the background. Equation 2.4 implies that one can assign a signature to a simple k-dimensional loop. Man, am I gonna give up here? Like, I'm so lost. Let's read the conclusion and see what they say. No, dude, I don't get this. I gave it a fair shot. I refreshed myself a little bit on solving systems of ODEs. I think to understand this properly, I would have to go into these references here, but I don't want to do that right now.